You've added QC-CALC real-time data collection software to your measuring machine. It works great. You can now collect data in real time, perform process capability, and gauge R&R studies. Tools are available to help you filter or group the data to isolate data streams. You can detect trends and generate all kinds of reports. At a glance, you can tell if the process needs attention. It's a great engineering tool. Unfortunately, QC-CALC does not interpret the results and tell you how to react to the information. If the process needs attention, what needs to be done to fix the problem? How do you react? In this example, I've collected data from a turning process. Most of the dimensional items are green, which means I'm in spec. You'll notice some of the dimension items are red, which means I've exceeded the spec limit. I'm running outside the spec limit. And some of them are yellow, which means I'm close to being outside the spec limit. If I'm an engineer familiar with the process, I can probably figure out what to do by looking through the data and making a decision. If I'm an operator on the shop floor, I don't have the expertise or the time to interpret this information. This problem is magnified with less experienced machine operators. I would like to introduce the Reaction Plan Manager++ software package. Reaction Plan Manager++ will analyze the data collected from QC-CALC and tell you how to react in real time. It gives you specific instructions. For example, adjust the cutter comp by 5 thousandths. It's like having an engineer available 24 hours a day, 7 days a week, looking through the measurement results and deciding what to do. This application is an RPM training CMM. Clearly, we don't have the time to put a part on a coordinate measuring machine and measure it. So we use this simulation software to simulate measuring a part on a coordinate measuring machine. I can pick a particular simulation and then click on the Inspect button. In this case, I'm going to use the RPM++ turning process. So if I click on Inspect, it's as if I were measuring a part on a coordinate measuring machine. I'm going to measure a part and watch what happens. The data went to QC-CALC Real-Time. QC-CALC Real-Time updated the charts and passed the data on to the Reaction Plan Manager++ software for data analysis. Reaction Plan Manager opened up the appropriate solution, did an analysis, and now it's giving us the instructions telling us what to do. The operator needs to adjust tool 1x offset by 0.0043. He also needs to adjust the tool 2x offset by 0.0042. This data was collected from machine A. Since the background color of this is with yellow, that indicates that it has a warning severity. You're probably wondering, why is this yellow and QC-CALC has some red and yellow dimensional items? Well, the Reaction Plan Manager, you're going to monitor and key off of the characteristics that influence the process. So if you make these adjustments, it'll probably correct all of the other dimensional items that are marked in red. It's also important to note that all this happened automatically. The operator just simply measured this part on the coordinate measuring machine, and he's getting all this information in real time automatically. I've hidden the other applications so we can focus our attention on the Reaction Plan Manager++ software. When you start the software, it defaults to what we call the view mode. The view mode is what the operator on the shop floor sees. You'll notice there are very few buttons on the left-hand side. It's done that way by design. The fewer the buttons, the easier it is to use. If I were an engineer and I wanted to develop a solution, I could enter what we call the edit mode, and the edit mode provides tools to let you develop and edit a solution. Below the control buttons are a list of reaction plans. A reaction plan is the result of an analysis of a group of data. It's kind of like a filter in QC-CALC. Here you'll see we have 5 different reaction plans. If I want to view a reaction plan, I just simply click on the reaction plan I want to view, and it brings it to the forefront and I can see it. Notice they are all color-coded. The color code represents severity levels. The orange flag represents the most current data that has been read. So the most current data is for machine A. What's nice about this list, I can at a glance tell what's going on with my machines out on the floor. From this list I can see machine E has got some severe issues. I probably need to focus on whatever the problem is with machine E. The rest of the viewing area is information related to the active reaction plan. Now if I'm an operator and I follow these instructions, I'm going to go out and make an adjustment on my machine, manufacture another part, measure it, and it should fix the problem. Clearly I don't want to mix old data with after the adjustment data. If you press this button here, which says press button if adjustment made, that will reset the part counter for these dimensional items, so it won't mix the old data with the new data. When the operator presses that button, that event is logged in a log file. And if you press this output events button here, you can see the log file. Now in this log file we only have 2 events. And I can read through them and see when they were done and what was displayed to the operator at that time. And the idea behind this is if I'm working on a machine and I have the same issues with this machine, maybe it requires some additional preventive maintenance, or you may need to have somebody come in and look at that machine. The checkboxes in the upper right hand corner control what is displayed by severity level. In this example, we're only looking at the dimensional items that have a warning and critical severity level. If I check the normal checkbox, it will show us all the dimensional items in the reaction plan. Now notice I've got 3 tabs down here. I've got part fixturing, tool 1 and 2 offset, tool 1 and 2 Z offset. These are organized by adjustments. If I want to see specific information about each one of these adjustments, I just simply click on the corresponding tab to get that information. Most users prefer to have that unchecked because they don't really need to see the dimensional items that do not require an action. They only want to see the dimensional items that they have to go do something. This reaction plan is being displayed in what we call the detail view. The detail view includes pictures, and the dimensional items have leaders that point to different parts of the picture. In this example, it's pretty clear what's going on. This dimensional item is controlling the tool 1 outer profile of the snout, and this dimensional item is controlling the tool 2 grooves. If I'm a new user, this is great because this is something I can relate to. It's a great training tool. If I'm an experienced user, this might be a level of detail that's not really necessary. You can switch from the detail view to the summary view. The summary view gives you the same information, but it gives it to you in list form, so you just follow the instructions from the list. What I've showed you so far is from an operator's point of view. It's really pretty simple. He just follows the instructions. Data flows from QC-CALC Real-Time into Reaction Plan Manager++. It does an analysis, gives him the instructions, and he follows them. What I want to do now is talk a little bit about how you do some of the calculations. Now I'm not going to get into how to edit a solution. That's beyond the scope of this demonstration. I just want to give you an idea of some of the different types of calculations you can perform. The goal for an engineer is to take his knowledge of the process and put it into a solution. Once he does that, the solution becomes the primary resource that operators can use to get process information. This frees up the engineer because he no longer has to spend as much time supporting the floor, because the operator can just use the reaction plans to get the information they need to make the appropriate adjustments. Maybe another way of thinking about it is that a solution is really a storage place for process knowledge. I'm going to check the normal severity so we can see the entire reaction plan. Now I want you to remember this is a simulation, it's really not real. It's designed to show concepts. This process is a turning process. This part goes onto a chuck, it spins up to speed. One tool machines the outer profile, which includes this flat surface here. A second tool machines this groove and that groove. So we're interested in how the part is fixtured. We want to make sure that it's fixtured properly. We want the tool to have the proper X adjustment, which is this way, and we want to make sure the tools have a proper Z adjustment, which is this way. Let's go back to tool 1 and 2X offset, and let's talk about the pulley snout diameter. The instruction here, adjust tool 1X offset by 0.0043. The key to a reaction plan is the dimension item. The dimension item determines how the data is analyzed, the instructions the operator sees, and when the operator sees the instructions. In this graph, you'll see white and blue dots. They represent part data. The white and blue dots combined represents the process info, and you'll see statistics associated with the process info. The blue dots represent the last run info, and you'll see here some statistics representing the last run info. The triangle represents the last run average for the blue triangle. The white triangle represents the process average. The engineer will decide how many total parts to keep. He'll also decide how many parts should represent the last run average. The data flows from top to bottom, so the top data is the latest information, the latest parts. The way it works is the data flows, a part is measured, data flows into the dimension item, the calculations are performed, and it's compared to these rules. If any of the rules are violated, that triggers a different reaction or a different set of instructions. This dimension item triggered a percent of tolerance rule violation. So our adjustment instructions are based upon whatever the engineer decided to put in for the verbiage for that rule violation. Now I want you to notice the last run correction is 0.00043. However, the last run info, the deviation from nominal, is 0.00087. This is half that deviation from nominal. Also notice the sign. You would think that this would be a minus sign because you're trying to move this average back to the nominal target, but it's positive. The engineer configured the logic for this dimension item to calculate the correct adjustment amount for this particular tool. So he flipped the value and he divided the deviation amount, the deviation from nominal, in half. That's how the engineer decided to do the X offset adjustments for tool 1 and 2. Let's talk about tools 1 and 2 Z offset. To do that, I want to change to a different reaction plan. Let's go to machine D. Now the way this works, tool 1 is cutting this outer profile. If you adjust this Z, it'll adjust this height. Well, if you look over here, the tool 2 groove is related to that surface. So if I adjust tool 1, it will impact tool 2 adjustment here. So in other words, if I make an adjustment to this dimension item, I really need to make an adjustment to this one as well, because it will influence tool 2. So tool 1 and tool 2 are linked. That is actually a pretty common occurrence in the machining world. I'm going to uncheck the shrink to fit so you can actually see the dimension items a little bit better. The pulley clearance surface triggered a percent of tolerance rule violation. So we have this instruction here to adjust this tool by this amount. You'll notice the snap ring groove also has triggered a percent of tolerance rule violation. It's yellow, and it's giving us an instruction to adjust by almost the same amount. If you look closely at this dimension item, it's almost on target. Well, what's happened is these two dimension items are linked, so when this event occurred, it added what we call a process shift to this data. And that little hidden triangle represents the process shift amount. So now it's telling us to make an adjustment here as well. The two are linked together. These are the type of things you can do inside the software. This just scratches the surface of the different type of analysis that you can perform. I'm going to unhide all the applications again so you can see QC-CALC in the RPM training CMM. Now let's assume I really am going to make an adjustment, a simulated adjustment. If I press this button here, I'm assuming I made the adjustment. Now you'll notice the blue line represents the reset. So now if I go to my simulator, click on the reset simulation, that simulates me actually making the adjustment. If I inspect another part, watch what happens. No adjustments, no adjustment recommendations. Go ahead and run the machine. So you can see it worked. Implementing the Reaction Plan Manager++ software solution will reduce machine downtime and improve quality by providing process control information. The software gives engineering a tool to capture and share process knowledge in a clear, consistent way, which significantly reduces the amount of time supporting the manufacturing floor. Shop floor personnel can use the software as a resource to get process adjustment information in real time. To learn more about the Reaction Plan Manager++ software solution, visit www.beckerqualitysolutions.com.